So welcome to the first session of the last afternoon. The session now is about thinking of all the things that we've learned and seen from other people. How do we actually, can that be made brought into practice? And we have three different speakers with different perspectives on this. So I hope that will sort of follow up from some of the discussions that we had before. So these are all three invited speakers, so 25 plus 5, but maybe we can eat a little bit into the coffee break and have a good discussion. Yeah, just a little bit. Obviously, the important bit about the coffee break is the last chance to put your poster stickers, because during the coffee break we will be counting the poster stickers, right? So don't do it until the last 5 minutes. And in particular, poster presenters, if you want to be there, if you think you might be winning, you want to be next to your poster such that we can take a picture of you. Okay, with that, let's start the session. So I'm very happy to welcome Professor Jae-Sung Lee, who came all the way from Korea. It's much appreciated that you did the effort. Jae-Sung is well known in the medical imaging community, both PET, SPECT, CT, lots of things. I was working at Seoul National University, but also, I guess, main founder of Brightonics. So many. Looking forward for a very interesting talk.
Okay. Thank you, Chris, for your kind introduction and having me today. So these are, my disclosures, and so this is the outline of my presentation, in which, I'm going to, start with why does, AI matter in nuclear medicine, and some challenges and considerations, which will be followed by the current and the emerging roles of AI in nuclear medicine. So let me start with why does AI matters in nuclear medicine. So as you know, the generation of our nuclear medicine images is based on the complex physics, but and our images is quite data intensive, because each pixel value of our images represents the functional and the molecular information. So however, our NM images is quite noisy and blurry. And as you know that the generation of three-dimensional tomographic data is usually time consuming. So in addition, the region-based quantification of our images is the labor intensive. So however, the demand for precise quantification is continuously increasing. However, there are some challenges and considerations in the application of AI technologies in nuclear medicine. So that is because mainly because the NM society is relatively small. So therefore, the open data sets and annotations so required for the AI, the algorithm development is quite limited. And many image acquisition and generation procedures has not been standardized. Of course, that the regulatory and ethical hurdles is quite high. So the clinical integration of many AI technology is still challenging in our nuclear medicine field. So I think this is why that the current role of AI in nuclear medicine is limited only the low level, the image processing and analysis techniques, which include the image enhancement, segmentation, and automatic quantification. So yeah, let me start with the noise reduction. So I think that the noise reduction is one of most successful field where the AI technology has been applied to the nuclear medicine field. Actually, that the posterior mean estimators such as noise to full and noise to noise has shown very the remarkable performance as illustrated here, and especially the long axial field of view data that has been provided by the Mikai ultra low dose challenge has contributed a lot in the advancement of this very important technology. However, the posterior mean estimators, such as UNet and CNN regressors, often yield the smooth and blurry output images. So that is why that so many of us are also interested in the posterior, the samplers, the generative models as a denoising technology. So one of the example of such posterior sampler that can provide more realistic imaging is the autoregressive generative framework that we have recently proposed to model NM images as a discrete state, the continuous time stochastic process. So actually in this approach, so we have assumed that the gamma photon accumulation in our projection data is kind of mixture of the Poisson process, and we have the trained neural network in a self-supervised manner, so using the least mode data to approximate the posterior mean of the Poisson rate and predict temporally evolving images. So based on this technique, we could generate random images from the pure darkness using the neural network trained with whole body bone scan images like this. Of course, we can also utilize this kind of generative model for the generalization of normal dose images from low dose image, by conditioning the neural network with low dose ones and mimicking how images evolve, as you can see here. However, I think that we should note there is some trade-off between the perceptual distance and distortion in the image denoising. So I mean, as I told you, the posterior mean estimators such as UNet and CNN regressors, to provide high level of phase list to the reference data. I mean that the high fidelity to the ground truth. But as I showed you, the perceptual realism of these posterior mean estimators is usually the low. And on the other hand, posterior samplers such as generative model and diffusion model, the yield the higher the perceptual realism, but faithful list to the reference ground truth data is relatively low. So therefore, I think the goal of our future investigation should be to reach the most balanced optimal point along this trade-off curve. Then how we can reach such the balanced optimal point in this the perception and distortion trade-off curve. So there would be so many different approaches, but in the recent the approach using the posterior mean rectified flow like model. So we have used posterior mean estimators as MMSE regressor in the first stage to lower the distortion. I mean the maximize the fidelity to the ground truth data. And in the second stage, following second stage, so we have enhanced perceptual quality using generative model while maintaining the closeness to the MMSE solution. For this second stage for refinement, actually we have chosen flow matching rather than diffusion model, because in flow matching we use OD based deterministic flow rather than the stochastic one used in diffusion model. And flow matching is also quite useful for the transformation between arbitrary distribution, although the diffusion model only transform from the Gaussian noise to the data. So this the good property of flow matching allow also fast and stable sampling. So in this slide you can see how we could reach such the balance optimal point. So in terms of perceptual distance and distortion using this posterior mean rectified flow like method. Let me now move on to automatic brain PET quantification. Yeah, actually, the brain PET, automatic brain PET quantification is clinically very important because we can enhance the inter-reader reliability and confidence score if we combine the visual reading of a physician with the quantitative tool, like BTX brain or Brightonix imaging. So usually, that this automatic, brain PET quantification is performed based on the spatial normalization of the brain images and predefined volume of interest as shown here. However, the conventional spatial normalization algorithm is usually the relatively slow because conventional method depends on the iterative estimation of deformation field required for the spatial normalization. And conventional spatial normalization is sometimes very unstable, especially for the atypical uptake patterns. However, on the other hand, the deep learning based spatial normalization can be very, very fast because we can directly estimate the spatially normalized images like this while deformation field required for the spatial normalization. And that this kind of deep learning based spatial normalization can be very robust to the atypical pattern because we can train this neural network with a lot of augmented data. So this slide compares the output of spatial normalization conducted using the conventional approach, the iteration based approach, and deep learning based one step approach used in our BTX brain software. So if you compare the input images and spatially normalized data and the standard template, I think you can appreciate the conventional spatial normalization methods such as SPM12 cannot overcome such a big difference between the input image and standard template in terms of the size of some anatomical structure. But you can see here the deep learning based spatial normalization could overcome such a big difference between the input data and the standard template. On the right side, so you can also see how robust this kind of deep learning based spatial normalization against very extremely low activity in brain regions. Actually, this patient suffered the previous stroke, so that's why she had very low, extremely low activity here. But conventional spatial normalization algorithm usually try to minimize that the extremely low activity region because it depends on the similarity between the spatially normalized images and the standard template with normal uptake distribution. But the deep learning based spatial normalization engine, so that was trained with a lot of augmented data. Could preserve the relative the shape and the size of this extremely low activity region. So this slide shows another example with extremely low activity, the region that has been well preserved in the spatially normalized images when we have used deep learning based spatial normalization technique. So let me now move on, further, the emerging roles of AI in our nuclear medicine field. Actually, there are, many different, the emerging roles of AI in our field, which include, the fast image reconstruction and CT-less, attenuation correction, the fast, voxel-based dosimetry based on the generative AI to replace, Monte Carlo simulation. And of course, that large language model and large multimodal model is also very promising technique that can be translated into the real clinical field. So among these, the emerging technology, I think CT-less attenuation correction is the method that has been most widely investigated by us. So therefore, that there are many different approaches to achieve this CT-RIS attenuation correction. But that our proposal was to combine the simultaneous image reconstruction and deep neural networks. Actually, in this method, so we produce the rough estimate of activity attenuation maps using the MLAA simultaneous reconstruction that is augmented by good time and resolution of current state of art path systems. And then these rough estimate of activity and attenuation map are given to the deep neural network that was trained to provide CT like attenuation map. Yeah, actually, this combination of simultaneous reconstruction and deep learning has several advantages over the CT-based attenuation map. For example, so we can avoid the beam hardening, the artifact of X-ray that has broad-beam spectrum, because that our attenuation map is generated based only on the monochromatic gamma ray using the emission path data. And because that we don't need X-ray CT data for attenuation correction, so we can also avoid emission and transmission the mismatch artifact, and we can also prevent CT truncation artifact that is caused by the limited transaxial field of view of X-ray CT that is smaller than PET field of view. We can also utilize this kind of CT-RIS attenuation correction for the phase matched the AC in the gated path, so without acquiring the additional X-ray CT images. And we can also utilize this high quality attenuation map generated using simultaneous reconstruction and deep learning for the estimation of deformation field between the gate frames like that to make the motion free emission data as shown here. Of course, we can also use other simultaneous reconstruction method like MLA-HF, and we can also utilize the unbiased attenuation map created using the intrinsic radioactivity from LSO scintillation crystals, as illustrated in these publications. However, I think that the generalization of this simultaneous reconstruction and deep learning based CT-RIS attenuation correction is still challenging. So that is because the MLAA and other simultaneous reconstruction algorithms is affected by the severe crosstalk artifact between the activity and attenuation data. So mainly because of the limited time and resolution of current path systems. So for example, so as you can see here, so these are the attenuation map generated using the MLAA simultaneous reconstruction algorithm. So you can see so there is some the severe crosstalk artifact that depends on the radio tracer that we have used for generation of these images. So that's why that we have explored several different methods to mitigate this crosstalk artifact shown in the MLAA the generating the attenuation map and activity map. And one of such method is utilizing the style encoder in generator of GAN neural network. I mean that that using the style encoder, so we could generate style vector of input attenuation map, and then we trained single the generator to reflect this style vector to mitigate effect of the crosstalk artifact. And another simple but very powerful method that we are now investigating is the utilization of spatially varying gamma field augmentation to make the deep neural network to be more robust to the such crosstalk artifact shown in the attenuation map. So actually, that in this method, we have augmented MLAA the attenuation map input. So based on the voxel-wise the gamma field correction. So using this gamma gamma correct the spatially varying gamma field correct the image, we can generate a lot of input images that mimic the crosstalk artifact shown in the attenuation map. So in this slide, you can see actually these are the MLA generating attenuation map from the FDG data, and these are the augmented the images using the spatially varying gamma field modification. So they looks they show some patterns that mimic the the crosstalk artifact that usually shown in the simultaneous reconstruction. So using those data, so we can just simply train the simple deep neural network that can be more robust to this kind of artifact. So this slide shows the result of the kind of investigation. So please note that the deep neural network used for the generation of attenuation map was trained only using the FDG data without any other tracer data. But it has shown very high the performance in terms of the PSMR, NR relative to the CT-based attenuation map for all of unseen the radio tracers that we have used. Okay, and our that the SVR analysis has also shown very high the correlation between the the deep learning based attenuation correction and CT-based attenuation correction. So let me skip this. Okay. Then let me move on the last topic, the Monte Carlo simulation. So as you know that the Monte Carlo simulation is very useful computational tool for our nuclear medicine, the imaging and research that include the image-based radiation dose estimation, the physical artifact correction and detector and imaging system optimization. However, as you know, the main drawback of this Monte Carlo simulation is its very long computation time. For example, that the Monte Carlo simulation can provide very accurate the voxel level dose map like this in the voxel based dosimetry, but it has not been the widely accepted in the clinical setting, mainly because of that long computation time. But in this, our very early studies, so we have shown that, deep learning can, generate the Monte Carlo, the equivalent, dose rate map that was trained using only the activity and attenuation map and Monte Carlo generated, the dose maps like this. Another, very interesting approach would be the optical simulation for scintillation detectors. Actually, the Roncalis group in UC Davis, has used GAN neural network to predict the optical photon distribution made by Monte Carlo simulation of a given gamma interaction position to accelerate the optical the simulation like test by up to 2 orders of magnitude. But we have experienced that this GAN-based model has some limitation in the generalization and the scalability. So that's why we have explored several different methods, and so finally that we have used flow matching as a stable and scalable the alternative to GAN for this kind of the optical simulation like task. So this slide shows how flow matching works. Yeah, in the flow matching, we define the velocity field. I mean that we define the particle motion in space-time that bridge two distributions. So in this case, the source distribution of this transformation using the flow matching is a multivariate Gaussian distribution, and our target distribution is the terminal, the photon state, including the instance the position and the instance angle of a photon at the end of scintillation crystal. I mean that at the interface between the scintillation crystal and the photosensors. And then that we train the neural network to learn this the velocity field, And in the inference stage, so we generate samples by solving this ordinary equation, differential equation. So this slide compares conventional optical simulation and OptiFlow, our method based on the flow matching. So in the optical simulation, so we can sample those terminal photon states from their distribution via physical modeling, as you know. But in the our optic flow method, we sample these the terminal photon state via the random mapping. So we can also scale up this approach, this neural network for diverse settings by conditioning the our neural network with various different conditions such as scintillation crystal type, size, and scintillation, the interaction position, and the gamma energies, surface treatment, or something like that. And the photon observations that we generate include the instance position and instance direction, the photon energy and propagation time, or something like that. Okay. So in this very beautiful slide made by my PhD student Sang-Jin, actually that the position and the direction, the propagation time of incoming photons varies according to the scintillation crystal dimension and interaction position, as you can see here. And so this slide compares histogram of instance position that were generated using the Monte Carlo simulation and our OptiFlow method. And so these are the histogram of instance directions generated using Monte Carlo and our OptiFlow method. And so these are the energy and the propagation time distribution, which matched with each other very, very well. Okay, so let me sum my presentation. So as I showed you, so AI has enhanced the image quality and quantification of our nuclear medicine. And there are many emerging technology that is refining our field. And finally, I believe the collaboration across our society will accelerate the advance in the AI application. Thank you. Thank you for your attention.